general process. Stop me if there's anything unclear. You should have learned this before, but in case there's any confusions, let me know. So this is the example. For instance, you want to prove the sum of r power k from k being 0 to n. This is true. Then what should you do? Right. Okay. So what should you do? You start from n being 0. Okay. I'll just talk about it. We start from n being 0. And when n is 0 on the left-hand side, what is the value? So it's only r power n, power 0, right? Which is 1, right? The left-hand side is 1. And then for the right-hand side, r power 0 plus 1, which is r minus 1 over r minus 1, so it's also 1. Then we can conclude that p of 0 is true. Are you with me? So the base case is correct, is true. Then what you're going to show? Assuming p of n being true, you want to show p of n plus 1 being true. I think I can maybe write it here. So step one, you show that p of 0 is true. It's done, pretty easy. Because when n is 0, the left-hand side is 1, the right-hand side is 1, no problem. And step 2 is the inductive step. You want to show that if p of n is true, I can show you p of n plus 1 is true. Okay? And this statement is about p of n. And you want to use this statement to show that p of n plus 1 is also true. And how does it work? We start from the left-hand side. When you replace n with n plus 1, the left-hand side is the sum over k being 0 to n plus 1. Maybe I should use a microphone. I think when I look at the screen, my voice can be a bit low. Is that okay? Yeah. So we want to show that you replace n with n plus 1, and this statement is also true. So how do we do that? The left-hand side is now k being 0 to n plus 1 r power k, which is the sum over k being 0 to n r plus r power k plus, this is together, r of n plus 1. Okay? This is the left-hand side when this is the left-hand side for the n plus 1 case. Are you with me? And you want to show that this part for n plus 1 is the same as this guy. Okay? So I'm not continuing, but you can see that following this mathematical induction, you can prove this statement is true. Should I continue? Okay, I can do that. So here it is the n plus 1 case for the left-hand side. And you want to show that the right-hand side for the n plus 1 case is the same as this value. And for the right-hand side, n plus 1, it will be r n plus 2. R arc n plus 2 minus 1 over r minus 1. And you want to show that this one and this one, they are the same. How are they the same? Is there a chalk anywhere I can use? You know where I can find one?
Okay, drawers in the desk?
Drawers? No.
Or that behind the actual board?
Here? No. Okay, let's see. It's a bit hard to write on the screen. Okay, I will, should I maybe upload a video later? I think that's too much. Any of you has a chart? Yeah, where?
Yeah.
No? Okay.
So like the projector, can you do it on? Like can you say
Oh, here? But I don't have a piece of paper. Let's see.
Here.
Okay, yeah, thanks. Maybe just, I'll just take this. Yeah. Thank you.
Yeah. Did you take numbers from the screen?
It's my first time using it.
So if I can that's exactly what I did in the systems. That's the one thing. It's exactly we did a whole fucking week on that side of it. That's cool.
Good.
I think it's too much.
Okay.
Just on top. Like there should be knobs on one side.
Like this. Okay, great.
Are you just rearranging the algebra on the left-hand side such that
Alright,
it's
so
equal to the right-hand side?
We want to show that
What? Thing to pay
the
attention.
sum
Fuck yeah.
k being 0 to n r power k equals r n plus 1 minus 1 over we want to show that this is true. And we start from the base case. And for the base case, let's consider n being 0. And when n is 0, the left-hand side, k being 0 to 0, r power 0. The left-hand side equals 1. This is a left. And for the right-hand side, it's a r plus 1 minus 1 over r minus 1. This is also
I get this. It's crazy. I get, okay. Thank you.
this
Give me
is
a
the
second.
right-hand side. So then we can conclude that so the base
In the base case?
is true. So this is step 1. And step 2 is the inductive step. And we want to show that if P of n is true, then we can show P of n plus 1 is true. This is what we're going to show in this inductive step. And what does this mean? Pretty much when we say P of n being true, we are pointing to this equation. Right? We're pointing to this equation.
Oh,
So
so you're
we
setting
want to
P of
show
n equal to
that
P of
when
n
we
plus 1 and
replace
then doing the
n
algebra
with n
such that
plus
P of n
1,
is equal to...
this guy is still true. Or technically, we're trying to show the sum of k being 0, not to n, but to n plus 1. This is the n plus 1 case. For the n plus 1 case, from k being 0 to n plus 1, r k, we want to know, is this equal to r n plus 2? Because we are replacing this guy, the n, replacing it with n plus 1. So now it's n plus 2 minus 1 over r minus 1. I'm using this tricky symbol to show that this is what we're trying to show. Is the left hand side the same as the right hand side? Then what are we going to do? So for this guy, because now it's k being 0 to n plus 1, it is the same as k being 0 to n r power k plus r power n plus 1. Is that true? No problem. As a result, this guy is, we borrow this equation. So it's going to be, we replace this guy with this part. So it's going to be r n plus 1 minus 1 over r minus 1 plus r power n plus 1. So this is the left-hand side for the n plus 1 case. Okay, this is the left-hand side of the n plus 1 case. And we want to see if this guy is the same as this one, right? Let me just put them together. So now we need to show this r n plus 1 minus 1 over r minus 1 plus r n plus 1. Is this the same as r n plus 2 minus 1 over r minus 1? So this is what we're trying to show here. If this is true, then we can draw the conclusion that this statement is generally true for any arbitrary number of n. We can draw that conclusion. So get back to this. Is this statement correct? So what are we going to do? There's this r minus 1. Let's just get rid of it. So we're trying to show r n plus 1 minus 1 plus r n plus 1 r. I just multiply this r minus 1 on both sides, nothing special. And for the right hand side, it's r n plus 2 minus 1. So as long as this statement is true, we are done with the proof. Okay? And the left hand side, we continue. It's r n plus 1 minus 1 plus, putting them together, is r power n plus 2 minus r n power n plus 1.
Just move it up just a little bit.
Okay. And is this the same as r n plus 2 minus 1? Are they the same? So they're the same, right? So then we are done with this second step. We just get rid of this one and this one, then they're the same. So we are done. Just want to mention that this tricky symbol is pretty informal. So this is to help you understand the proof process, but officially you don't write it this way. Okay? But that's fine. If you write it, we understand. So the important thing is that there are two steps, the base case and the inductive step. The base case showing the n being 0, and then we show p of n plus 1 is true from p of n. Any questions? Okay. All right, so this is an induction proof example. Another example, say we want to show for any n the same as 0 or equal to or greater than 0, n is smaller than 2 power n. So similarly, we have two steps, the base case and the inductive step. For the base case, n is 0, so the left-hand side is 0, the right-hand side is 2 power 0, and 0 is smaller than 1, so it's true, okay? And then you want to show that assuming P of n is true, can we prove that P of n plus 1 is true? This is an inductive step. So we assume n is smaller than 2 power n. We want to prove n plus 1 is smaller than 2 power n plus 1. So the reasoning process is pretty straightforward. N plus 1 smaller than this guy. We want to show that this is, I'm a bit lost. So we want to prove n plus 1 is smaller than 2 power n plus 1. And we know that n plus 1 is smaller than 2 power n plus 1. Where is this from? It's from the P of n case. Right? It's from the P of n case. We are assuming this is true. And we add 1 on both sides. We have this. And we also know that 1 is smaller than 2 power n. So from here, this is true. Then we continue. There are two 2 power n. Put them together is 2 power n plus 1. So altogether, we know that n plus 1 is smaller than 2 power n plus 1. So we show that the n plus 1 case is also true. Is that clear? Okay. Actually, I just remember something. So I should have mentioned it. Actually, I did mention it in the introduction video. We have a Slack space, Slack workspace. I think last time I checked it, there were only 20 or 30 students on it. But this whole class has more than 80 students, meaning that most of you are not there yet. So do you have difficulties joining the Slack workspace?
There's 72 now.
I'm sorry?
There's 72 members now.
Really? Oh, that's great. So, yeah, that's great. Still, I think some of you are not there yet. So, there's a general channel, there's a homework channel. You can post questions there. And the way it works is that we have 2 TAs and myself. And during our office hours, we will allocate some time to answer questions on the Slack workspace. So if you post a question, give us maybe, I don't know, 12 hours at least. If there's no response, you can email us and say, hey, there's something unresolved on Slack, you may want to take a look, something like that. What else? Please do not send me direct messages on Slack. So as you can imagine, there are 70 students, and if you write me a direct message, I clicked it. If I don't have time to answer it right now, then it will disappear, because it's very hard for me to find who among the 70 students asked that question. Does that make sense?
Oh no, you gotta go.
So if you post it, if you really have something, you have something to ask, but you don't want to share with other students, drop me an email. Okay, it's automatically on my to-do list. I'll process it there. But direct messages on Slack, sometimes you just I don't know. It's very hard for me to go there and see which question is not answered yet. All right. This is another example. So generalizing induction, still two steps. The base case, we prove that P of C rather than P of 0. So if n is starting from 0, then the base case is P of 0. But it's possible that you are starting n from a non-zero value, then generally it's like P of C. And from there, you do the inductive step, which is to prove P of n plus 1 being true from P of n. Just another example. You can read it offline. The first homework will be on mathematical proof using induction. So there will be maybe 4 questions. And in general, I try to give you 2 weeks to work on each of the homeworks. And totally, we are going to have 8. Okay, 8 homeworks. There will be 8 homeworks, and each of you work on it individually, and there will be 4 programming assignments, and you can form a 2-student team to work on it, and only 1 student makes a summation. Again, I mentioned in the video, but let me highlight it again. If you work in a team, do not make multiple summations. It happened before that maybe student A worked with student B, and student A makes a summation maybe at 11 p.m., and student B made a summation at 11:30, but it turned out that the 2 summations are different from the same team. Then it's tricky for us to decide which one to grade. So just make 1 summation, mention your teammate name in the README. Is that clear? Okay. And if it's late, the late data apply to both of the students in the team. Okay. And it's optional for you to work in a team. It's also your responsibility to find a good teammate. Okay. So it's, of course, you know, some of you are more helpful, supportive than the others. But if you work with, you know, a student that is not that responsive, I can't help. I can't say that you work with this one. It's your job to convince your classmates that you are a good teammate, so you can maybe work with you find your own good teammate. So technically, they are not really, the 4 programming assignments are not really about programming. So you are going to use a tool to solve some automata problems. So you're going to use some software, but you don't have to do programming, okay? You're going to use your computer, use the software, but you don't have to do C or Python or whatever programming languages. Another thing I want to mention today is the pigeonhole principle. So this principle states that if there are P items and we put them into H pigeonholes and P is bigger than H, then at least one of the pigeonhole must contain more than 1 item. Okay. Later, we are going to use this principle to do some proofs. So for instance, you say, hey, there are transitions maybe among 10 states, but I can prove that there must be more than 10 states, and then you can show that maybe 1 state must represent like 2 instantaneous descriptions or something. So this is the principle that we will revisit a few times. And the point is that if there are P items and you put them into H pigeonholes, and then at least 1 pigeonhole must contain more than 1 item. did we say anything about any pigeonhole being empty? No, right? So it's possible that some of the cells are empty. We are not saying anything about that. All we are saying is that there must exist at least one cell that contains more than one item. That's the only statement we're trying to make here. So suppose you have 3 pigeonholes here and 4 pigeons, and we can draw the conclusion that there exists at least one of the cell that includes more than one pigeons. That's the conclusion we can draw. So as an example, we apply this principle to this application domain. We say there are 10 people swimming in a lake, and we prove that at least 2 of them were born on the same day of the week. And in this case, what is the pigeonhole? Yeah. Each day of the week, right? So we have 7 holes. And then what is the atom, or what is the pigeon? The people, right? So in this example, you have 7 holes but 10 pigeons. Then we can conclude that there must exist at least one day where there are at least 2 people born on that day. Okay, so we're going to later use this principle in our proofs. So we're supposed to end at 4:30, right? It's a 1-hour meeting and 15 minutes. Next, I'll talk about languages. So I want to say it's very straightforward, but there are quite a good number of new concepts, okay? So there isn't anything difficult, but you probably see a lot of the new concepts. And what I'm trying to say is that you probably cannot remember everything, but I'll upload the slides onto the course schedule page, and you need to revisit. Maybe later you say, oh, there's a concept, what is that, symbol. So technically, what does a symbol mean? Go back to the slides and there are definitions here. So a language is a set of strings. When we say a set, there is no order. Okay, there is no order. A language is a set of strings, and the string is a sequence of symbols from some alphabet. When we say a sequence, there is a order there. Right? There's a sequence of symbols. So then we can say the language is a set. The language is technically a set. And in this example, the set is of size 3. There are 3 strings, cat, dog, and house. Okay? And each string is a sequence of symbols. So cat is a sequence of 3 symbols, C-A-T. And C-A-T, each of them is a symbol in the alphabet. So C-A-T, each of them is a symbol in the alphabet. So you should remember, language is a set, string is a sequence, and string is a sequence of symbols, and all the symbols together form alphabet. Okay? So nothing really difficult, but we're going to use those concepts later. Languages are used to describe computation problems. This statement can be a bit confusing now, but later, when we talk about DFA, NFA, and Turing machines, you understand what this means. So languages are used to describe computation problems. So primes, it's a language, right? It's a language. It's a set that includes all of the strings. And this string includes only one symbol, this string includes only one symbol, but this guy includes a sequence of two symbols, 1 and 7. And all the symbols together form this alphabet, 0, 1, 2, dot, 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 9. And even is another language generated using the same alphabet, okay, the same alphabet. Should I say that? Yeah, we can say that. So we use this alphabet to generate this language. But this even language is not using all the symbols from the alphabet, right? It's no, actually it is using all the symbols from the alphabet. So even if it's an even number, it's probably 12, say 1, 2. So it is using 1, 2, and all the symbols from the alphabet. Computation is translated to set membership. So example computation is number x prime, and then what are you going to do? You check whether x belongs to this language. And since the language is in the form of a set, you can mathematically check whether an element is in a set. And then you can say x is a prime number or not. An alphabet is a set of symbols. The language is a set of strings, and the string is a sequence of symbols. So again, nothing really difficult, but just get used to the new concepts. So example strings, A is a string, AB is a string, ABBA is a string. And we can say that, we can define a variable and say U is a variable, and this variable only includes maybe this AB string. So we introduce the variables so that later we can define some operations among those variables. Maybe we concatenate U and V, then we can generate a new string. Excuse me. Okay. So decimal numbers alphabet includes 0, 1, 2, dot, 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 9. And using this alphabet, we can generate different strings. This one. And binary numbers alphabet is including only 0 and 1. And we can use that to generate different strings. This is another example, unary numbers. Now we have only, we have the alphabet that includes only one symbol, okay? We usually do not discuss an alphabet that is empty, okay? So the alphabet is usually non-empty, but it's possible that a language is empty. A language can be empty, a string can be empty, but the alphabet cannot be empty. So this is the language of the unary number. It can be 1, 1, 1, 1, 1, 1, and decimal number 1, 2, 3, dot, dot, dot. So after introducing W and V as the variables, we can make some operations between the variables. And one of them is concatenation. So we can say W is a variable that is a sequence of A symbols, and V is a variable that is a sequence of B symbols. And then we concatenate this string and this string all together. We can generate A, dot, 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 a number of A's followed by a number of B's. So this is a resulting string. And if one string is ABBA, another string is BBBAAA, then we concatenate both of them. It's going to be ABBAB followed by BBBAAA. Okay, so this is the first string operation, concatenation. Next, we're going to talk about a few of them. So concatenation is one, and reverse is another one. So if the string is AAA dot dot dot, a number of A's, and the reverse will be the same, right? It's the same. And for another example, A, B, A, B, A, A, B, 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 the reverse will be B, 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 A, A, A. You're reading it from the right. So that's a reverse of it. And string length. So for n A symbols, the length will be n. And for A, B, B, A, the length is 4. For A, the length is 1. All of these are pretty straightforward. It's just later when we say what is the length of a string, you know what that means. That's pretty fun. Length of the concatenation. If the length of U string is 3 and the length of V string is 5, then we concatenate both of them. Altogether, the length will be 3 plus 5, being 8. Okay, 8. It's possible that we have a string that is of 0 length. Then this is an empty string, and we use what is that? Epsilon, right? We use epsilon or lambda to represent empty string. So we mentioned both because depending on the textbook, depending on context, people used to use different symbols. Okay, so later you will find some of the symbols are a bit different from the textbook you use. In the slides, we usually say epsilon, but in the textbook, probably something different. So it acts as a neutral element. So if a string is empty, then the length is 0, and you concatenate empty string with W. The resulting string is the same as the W. It doesn't add anything. The same story, empty followed by ABBA. The resulting string is ABBA. Straightforward. So if you are given a string ABBAB, then we will say AB is the substring of ABBAB. And for ABBAB and BBAB is a substring of it. Okay, so substring length is definitely smaller than the original string's length. So this is a substring. Prefix and suffix, there isn't, I think it's pretty straightforward. If the string is ABBAB, then you can have the prefix as being empty, and then the suffix is ABBAB. And you can also cut it maybe here. Then you have AB and BAB. Okay, those are different ways of separating it.
So a string is not a substring of itself.
I'm sorry?
A string is not a substring of itself.
It is. Oh. So this is a case where ABBAB is a substring of itself.
So then the length of the substring can equal the length of the string.
Yeah, it can be equal. Yep. Did I say that it's smaller than that?
Yeah.
Yeah, okay, it can be equal to that.
Okay.
Thanks. Exponent operation, when you see a string, power n, it means there are a sequence of the W strings concatenated all together. So if you have ABBA power 2, then it's a ABBA followed by another ABBA. Okay? So later we are going to show you a language L power n that has a different meaning. So when you see this exponent operation, pay attention to the base. Is that a string or is this a language? So here it is a string, then it means W followed by W dot 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 altogether NW strings. And if it's W power 0, then it's empty. And ABBA 0, it is empty. And this is the exponent operation for strings. There's also the star operation. It is over alphabet. Okay, it is over the alphabet. When you see an alphabet star, it means a set of all possible strings from the alphabet. Okay, it's the start of the all possible strings of alphabet. So if the alphabet includes only A and B, then you can select nothing from the alphabet, then it's an empty string. You can select A from it, it's A, B, or maybe two A's, or two B's, three A's, and also you can say AB, BA, AAB. So any strings generated using the symbols from the alphabet that belongs to sigma star. Okay, sigma star. There's also this plus operation. It's the same as the star operation. The only difference is that sigma plus, it doesn't include the empty string. So this one is get rid of. So that's the only difference. Other than that, they are the same. Languages. Maybe you have 1 minute, so maybe we should stop here and talk about languages next time. So I'm still